So, you know me quite well. So you basically know that the transition from sort of an ergodic or an eigenstate thermalization or extended, whatever you want to call it, phase that we sort of we just assume we have that when we're doing regular stat mech, right?
Mm-hmm.
And then transitioning to a thing that's localized, which maybe there's a mobility edge which we could get into, or maybe it's just basically you increase some disorder parameter and then you go from everything is ETH to everything is not ETH. So this is my favorite transition. It's a transition that happens to the properties of basically all eigenvectors, or if there's a mobility edge, a lot of eigenvectors until you get to a certain point.
Mm-hmm.
Then you get all of them. So coming from in sort of a metal to insulator transition in some sense, coming from your background, a more perhaps you might have access to more phase transitions that would be interesting. What's your favorite phase transition?
Well, my favorite phase transitions, first of all, the thing is that when you study this kind of thing, I just find all of the phases of matter that we've discovered, all of the sort of phases of matter that are really governed by quantum mechanics, to be just totally amazing. I mean,
that's a fair statement. Yeah.
Superconducting phases are amazing. There are out of equilibrium phases, sort of dynamical phases. So you, for example, can have materials, semiconductors, where when you apply a magnetic field through the material, they exhibit what's called the Hall effect, a quantum version of the Hall effect. We can maybe talk about what that is if that would be interesting. But the upshot is that if you have a conductor and you have a current running, say, along the x-axis, and then you apply a magnetic field perpendicular to that, you actually get a current that begins to go transverse to that. And that's coming from the Lorentz force acting on the charge carriers. That's the sort of classical Hall effect. It was discovered in 1878.
Oh, that's interesting.
And then what people discovered was that in semiconductors, you can have a quantum version of this effect where the charge transport in the transverse direction is quantized. So it comes in steps, integer steps of the electron charge. And then in the I think in the 1970s or 1980s, von Klitzing discovered that you can have a fractional version of this effect. So you can have a quantum Hall effect, but where the charge transport isn't in integer units of the Coulomb charge, but is in fractions of a Coulomb charge. In other words, it looks like as if the electron has broken into pieces.
Okay, that's really
inside
interesting.
of this material. It's fascinating. And
that's
so
fascinating.
People then began, the first person to sort of correctly understand this was, or maybe the first person to propose a wave function that described this behavior was Robert Laughlin, the so-called Laughlin ansatz, we now call it. And it was later discovered that this physics is related in some deep way to the topology of the state of the sort of space of quantum states. And it's now just one example of many states of matter, which certainly exist theoretically, and some of them have been found in materials, and some of them are still being sought after in materials, real materials.
Yeah.
But phases of matter that are characterized by the sort of fundamental topology of this space of quantum states. And these phases of matter exhibit all kinds of remarkable properties. So the fractional charges is just one property. We call these anyonic excitations. So in three-dimensional space, people who do physics will know you have bosons, you have fermions, and bosons are particles where if I take two bosons and I interchange their position, the wave function looks identical. And fermions are particles where if I interchange their position, the wave function picks up a minus sign in front.
Yep.
And that's all there is. In three-dimensional space, that's the only kind of particle you can have. Those are the only two types of particle you can have. But in two-dimensional space, you can have these so-called anyonic particles, where interchanging the two particles, winding two anyonic excitations around one another, might result in the wave function coming back to itself, but with a phase out front, a phase that isn't just plus or minus one, but maybe could be some complex phase.
Yep.
Or perhaps you wind the two particles around one another and the wave function comes out to be some entangled mess of other states. And these anyonic excitations fundamentally arise because of the topological nature of the ground state. Topology is a property that is sort of a global property. If I have a mug, for example, and I imagine the hole where the handle of the mug is sitting, the topology of that, we would say that that's a surface of genus 1. So the genus is basically the number of punctures in your surface. And no matter how I sort of mold or shape or deform my mug, that hole where the handle is still sitting there. So for example, I could take the mug and I could deform it into the shape of a donut, where the hole in the center of the donut was the hole in the handle. Yeah. And from a topological point of view, those are the exact same type of surface. And so topology, in other words, is robust to these sort of perturbations. You can sort of stretch and deform and perturb your system, and a topological property of the system will remain invariant through all of those deformations. Mm-hmm. And so in these quantum phases that are topological, you can take external magnetic fields, all kinds of noise, you can take disorder, and no matter what you do, to within some reasonable limit, to within there's sort of an energy gap that is kind of protecting this topological order. And so whatever you do to the system within the bounds of that energy gap will protect this topological structure.
I see, okay.
And so this is a really appealing basis for quantum computing. Alexei Kitaev, I don't know if Alexei Kitaev was the first person to realize that, but I think he's one of the sort of visionaries who began to come up with ways of writing down models that exhibit this kind of topological invariance, which have excitations that you can do quantum computing on. Okay. And because of the fundamental robustness of the topology, the qubits, which would be your anyonic excitations, are going to be robust to environmental sources of decoherence that plague other attempts at instantiating quantum computation.